This video introduces Casimir-SAT, a physics-driven approach to satisfiability (SAT) solving. It leverages the concepts of vacuum dynamics and the Casimir force to transition between SAT and unsat regimes. The core insight draws on the Casimir effect, where restricted quantum vacuum fluctuations create physical attraction. Similarly, frustrated clause regions create computational gradients that drive the system toward satisfaction, causing coagulation. We move from discrete Boolean clauses to a continuous energy landscape using a differentiable energy functional. Boolean solutions correspond to global minima in this unit hypercube, allowing us to use Langevin dynamics to flow toward satisfaction. The fractional satisfaction function is the core mechanic, interpolating Boolean logic for continuous optimization. Intermediate values provide continuous gradients, and automatic freezing occurs when all relevant clauses are fully satisfied. The Casimir-like force emerges as a distance-weighted potential, concentrating stress at frustrated domain walls. This force drives the annihilation of domain walls and the coalescence of satisfied regions. The dynamics are governed by a modified Langevin equation, including the energy gradient, the Casimir force, and thermal noise. Annealing schedules control the temperature, leading to a sigmoidal projection and Boolean crystallization. Coagulation begins with a maximum entropy initial state at high temperature. Spontaneous phase separation occurs via Langevin dynamics, separating low-energy satisfied clusters from high-energy domain walls. We use spectral cluster detection. A weighted Laplacian encodes geometric proximity and gradient magnitudes. The Fiedler vector partitions variables into frozen clusters and wall variables, rigorously focusing computational effort. Phase 3 involves recursive coarsening and clause learning. Frozen clusters contract into supervariables. Clause learning at active walls reshapes the energy landscape, preventing domain walls from reforming, achieving a CDCL-like effect. The final crystallization phase involves cooling and shrinking. The remaining fractional variables, typically fewer than 20, are passed to a conventional solver for a final solution, leveraging the prior physical dynamics. SAT phase transitions correspond to domain wall scaling. We observe transitions from connected solution clusters through exponentially isolated clusters to the unsatisfiable phase, tied to clause density. In the dense phase, Langevin dynamics converge in expected polynomial time. In the fragmented regime, an exponentially small Fiedler gap automatically flags hard instances, turning algorithmic failure into a measurable physical observable. Our implementation in Crystal offers a 15 to 20 times speedup over Python. Casimir-SAT also achieves linear memory usage and high GPU accelerated scalability due to parallelized gradient computations. Casimir-SAT demonstrates a significant performance advantage on random 3 SAT, achieving a median solve time of 2.1 seconds, 6 to 10 times faster than MiniSat and Glucose, and a 94% success rate. Runtime analysis shows Casimir-SAT remains polynomial below the clustering threshold. It confirms that computational complexity emerges from genuine thermodynamic transitions, providing insights into the condensation phase. Extensions include a weighted max SAT objective. The approach also has implications for quantum annealing hardware, suggesting a near-term physical realization of Casimir-inspired computation using analog and quantum devices. Future directions involve theoretical proofs, machine learning integration for optimal scheduling, and extension to other nitrogen monophosphide complete problems. This positions computation as physics, where nature performs algorithmic work through free energy minimization.